In this video, we're going to take a look at how to do reaction stoichiometry. This worksheet is taken from the web and it's available on the Edmodo website. You can do your answers directly on the worksheet if you'd like to print it, or you can do them in your notebook neatly on loose leaf. If you choose to do it in your notebook, then be sure you write out the balanced equation, jot the question down, and then show your answer in the way that I'm going to do here. If you print it on your computer, then just do your work in the space. So this is reaction stoichiometry. In other words, we're going to be solving problems based on balanced chemical equations. In this first example, we have a reaction between ammonia gas, oxygen, and the products are water and nitrogen monoxide gas. And we see a balanced equation which says 4 moles of ammonia react with 5 moles of oxygen, producing 6 moles of water and 4 moles of nitrogen monoxide. The first question says, what mass of nitrogen monoxide would be produced if 2 moles of ammonia are reacted with excess oxygen gas? The fact that it says excess oxygen simply means that there's more than enough oxygen to use up all of this ammonia. So the ammonia is going to get used up completely, and therefore it will determine how much product we can make. So to answer this question, we're going to set up a string of unit multipliers. So we'll pay attention to significant digits and our units. We have 2.00 moles of ammonia that are going to be used up in this reaction. So we'll use a unit multiplier based on the balanced chemical equation to switch from moles of ammonia to moles of NO. The question asks what mass of nitrogen monoxide would be produced, so we'll first find how many moles there are. This ratio, moles of NO and moles of ammonia, is based on the balanced equation. Looking at the coefficients in the equation, we can see that 4 moles of NO would be produced from 4 moles of ammonia. So now we know how many moles of NO will be produced. We can calculate how many grams by adding one more multiplier, get rid of moles of NO, and switch that to grams of NO, and of course that would be the molar mass of nitrogen monoxide. 1 mole of nitrogen monoxide would have a mass of 30.01 grams based on a periodic table. Grabbing a calculator and paying attention to the significant digits, we have 2 times 4 divided by 4, which cancels out, 30.01, and we get 60.02 grams of NO based on my calculator, but we should have kept only 3 significant digits because of the 2.00. So we'll say 60.0 grams of NO will be produced. Okay. The 4s that came as coefficients, they actually are perfect numbers. They're not measurements. The balanced equation said 4 moles will produce 4 moles. So that's exactly 4. It's like they have infinite number of significant digits. So don't ever use the coefficients to round off your answer based on sig figs. Consider them to be perfect pure numbers. They have infinite sig figs. Part B, what mass of water would be produced if 4.00 moles of oxygen are reacted with excess ammonia? So this time it's the oxygen that will get used up because we have excess ammonia to react with it. Therefore, we can use the oxygen, the thing that got used up, to predict how many products will be formed, how much product will be formed. So we'll take the 4.00 moles of oxygen, which we know will be used up in this reaction, and we'll get rid of moles of oxygen, and we'll find how many moles of water would be produced. The question wants to know the mass of water, so we'll start by finding the moles of water. Then with one more unit multiplier, we can convert the moles of water to grams of water. The first multiplier, moles of water, moles of oxygen, is based on the balanced equation. It tells us that 6 moles of water can be produced from 5 moles of oxygen. The coefficients were 6 and 5 in the balanced equation. The second multiplier, grams and moles of water, is the molar mass of water. 1 mole of water has a mass of 18.02 grams. Grabbing a calculator, we look and see we should keep 3 digits in our answer. So 4 times 6 divided by 5 times 18.02 gives me, my calculator says 86.496. So I'm going to write 86.5 grams of water will be produced. Okay? So notice that we're calculating how much product would be produced, starting with the substance we know is getting used up. We know the oxygen would be used up because it was reacting with excess ammonia. There's more than enough ammonia there to use up all the oxygen. Part C, what volume of ammonia gas at STP, now as soon as I see that, volume at STP, I'm remembering that we know a unit multiplier that said there's 22.4 liters of any gas at STP for 1 mole. So 1 mole of any gas has a volume of 22.4 liters at STP, and that's a unit multiplier that we'll use in this question. So what volume of ammonia at STP do we need to react with 3 moles of oxygen gas? The first 2 questions gave us a reactant and asked how much product can we make. This third question is giving us a reactant, 3 moles of oxygen, and it's asking how much of the other reactant, the ammonia, do we need to react with that. So we'll take our 3 moles of oxygen, and using the balanced equation, we'll convert from moles of oxygen to moles of ammonia. And then using our volume unit multiplier at STP, we can convert the moles of ammonia into liters of ammonia. So from the balanced equation, there's 4 moles of ammonia that'll react with 5 moles of oxygen. And then 1 mole of any gas, including ammonia, has a volume of 22.4 liters at STP. So grabbing our calculator, it looks like we need 3 significant digits in the answer. So 3 times 4 divided by 5, and then times 22.4 gives me 53.8 liters of ammonia are needed. And of course, that's at STP. The fourth question, the fourth part of this first problem, wants to know what volume of ammonia, one of our reactants, measured at STP, do we need to produce 0.750 moles of water vapor. So this time we're asking how much of one reactant would we need to produce a certain amount of a product. We'll set it up in exactly the same way that we've done these others. We'll take the 0.750 moles of water that we know we want to make, and we'll first find how many moles of ammonia would we need. So we'll get rid of the moles of water, and we'll use our recipe, the balanced equation, to find how many moles of ammonia are needed. And then we can use that same volume multiplier to convert the moles of ammonia into liters of ammonia. Because we're at STP, 1 mole is 22.4 liters. You remember STP means standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere pressure. From the balanced equation, it looks like there's 4 moles of ammonia that will produce 6 moles of water. So grabbing our calculator, we want to keep 3 significant digits again, so 0.75 times 4 divided by 6, and then times 22.4, 11.2 liters of ammonia are required. Okay? Notice we need the balanced equation, has to be balanced, in order to get the correct ratios in our unit multipliers. So if you were given a question like this without the equation already balanced, you'd have to balance it first to get those ratios. Let's do one more question here. Pentane, C5H12, burns according to the following reaction. Now I hope you can foresee that later we'll get a question that simply says pentane is burned, and you would have to write the balanced equation yourself. You'd have to recognize that that's a hydrocarbon combustion reaction, then realize it reacts with oxygen, remember that it produces CO2 and water, and then balance the equation yourself to do the stoichiometry problem. Part A says, what mass of water would be produced when 100 grams of the pentane is burned? And again, assume that there's excess oxygen. In other words, assume that all of that pentane is burned up. So we'll take the 100 grams of pentane, C5H12, and we'll first convert it to moles. We'll get rid of the grams and switch to moles of pentane, C5H12. And now we can use our balanced equation to convert the moles of pentane to moles of the water. We're wanting to know what mass of water, so we'll first find how many moles of water. Then we can convert the moles of water to grams of water using the molar mass of water. So in the first multiplier, we want the molar mass of pentane, so 5 times 12.01 plus 12 times 1.01, and that's 1 mole has a mass of 72.17 grams. The second multiplier, moles of water and moles of pentane, that would come from the balanced equation. It says that 1 mole of pentane will produce 6 moles of water when it's burned. And the final multiplier is the molar mass of water. 1 mole of water weighs 18.02 grams. So grabbing a calculator, 100 grams of pentane divided by 72.17, this is the moles of pentane now, times by 6, this is the moles of water, and times by 18.02, this is the grams of water. It looks like I should keep 4 significant digits in my answer. 100.0 had 4 digits, and each of my molar masses had 4 digits. So my answer is going to be 149.8 grams of water are produced. Okay? When you're doing these questions yourself, be sure that you're setting them up exactly the way you see them here. The use of unit multipliers, showing the units and the formulas like I'm doing, paying attention to significant digits, and then putting a little tiny statement at the end. Notice I've been saying are needed, will be produced, are required, etc. That's how I'd like to see your answers laid out in order to get full credit. Part B, what mass of pentane would be required if you want to produce 90.0 liters of CO2 at STP? And again, assume that we have excess oxygen, which again means that this pentane that we're using will get used up completely. So this time we're given a product, the CO2, and we're asked how much of the pentane would you need to get that. So take your 90.0 liters of CO2 and think about what we'll do first. We can convert those liters into moles of CO2 because they were given at STP, so we know that 1 mole is 22.4 liters for any gas at STP. Now that we've got moles of CO2, we can use the balanced equation. We can convert from moles of CO2 to moles of the pentane, C5H12. And then finally it wanted to know the mass of pentane, so we can get rid of the moles of pentane and switch to grams of pentane. So the second multiplier comes from the balanced equation. 1 mole of pentane produced 5 moles of CO2. And the last multiplier is again the molar mass, but this time of pentane, which we saw earlier. 1 mole of pentane was 72.17 grams. Grabbing a calculator, it looks like we want to keep 3 significant digits, so 90 divided by 22.4, divided by 5, and then times 72.17, and I get with 3 significant digits, my calculator says 57.99375. To keep 3 sig figs, I'll round that off to 58.0 grams of pentane, and those are needed. Okay. Part C of the question asks, what volume of oxygen measured at STP would be needed to produce 70.0 grams of CO2, and assume that we have this time excess pentane. So again, assuming we have excess pentane simply means that all of the oxygen will be used up. So we will take our 70.0 grams of CO2, that's what we're trying to produce, and let's see how many moles of CO2 that is. So we'll get rid of grams and switch to moles of CO2. And then let's use our balanced equation to find out how many moles of oxygen we would need. So get rid of your moles of CO2 and convert to moles of oxygen. And then we'll figure out how many liters of oxygen we need at STP by getting rid of the moles of oxygen and switching to liters of oxygen. And now let's put the numbers in. 1 mole of CO2, this is its molar mass, is 44.01 grams. The balanced equation says 8 moles of oxygen will produce 5 moles of CO2. And then using our using the 22.4 liters for 1 mole of any gas at STP. So we want to keep 3 significant digits, 70 divided by 44.01 times 8 divided by 5 times 22.4 equals 57.0 liters of oxygen, and this is at STP, are needed. That's what you would need to produce 70 grams of CO2, assuming that you had excess pentane to burn up this oxygen. Alright, I said we'd do, that would be the last question, but you know what, let's squeeze one more in. This third question takes things up just one level of difficulty because it doesn't give us a balanced equation. How many liters of hydrogen gas would be produced by 5.72 grams of zinc in the single replacement reaction between zinc and hydrochloric acid, measured at STP? So let's start with a balanced equation. Zinc reacts with hydrochloric acid. The question gave us a clue that it's a single replacement reaction. Hopefully you would have seen that yourself just looking at those reactants. In a single replacement reaction, the zinc is going to go in and become, what's the charge on zinc? Well, it becomes 2 positive, right? So zinc, when it's an ion, is Zn2 positive. That means it's going to be attracted to the chloride ion here, which is negative, Cl negative, and the product, since Zn is 2 positive and chloride is negative, the product will be ZnCl2. And then the hydrogen will come out as hydrogen gas, and because it's one of the Hofbrinkel elements, its formula is H2. It's diatomic. So now to balance this equation, we can see we just need to put a 2 in front of the HCl, and we're balanced. So now we can go ahead and answer the question, what volume, how many liters of hydrogen do we need, will be produced when 5.72 grams of zinc react with excess hydrochloric acid. So let's take our 5.72 grams of zinc and first convert the grams to moles of zinc. Now we'll use the balanced equation to convert the moles of zinc to moles of hydrogen. And finally, using our volume, we can say moles of hydrogen can be converted to liters of hydrogen because the gas was measured at STP. The molar mass of zinc, 1 mole of zinc is 65.39 grams, I think. I'm going a little bit by memory there. I think that's right. And then from the balanced equation, 1 mole of zinc produces 1 mole of hydrogen. So that's pretty straightforward. And then finally, there's 22.4 liters of hydrogen for every mole of hydrogen at STP, standard temperature and pressure. So 5.72 grams of zinc divided by 65.39, this is the moles of zinc, and then times 1, that'll be the moles of hydrogen, and then times 22.4, we get, with 3 sig figs in our answer, 1.96 liters of hydrogen will be produced. And I probably should say at STP. So that's the volume of hydrogen produced from 5.72 grams of zinc. I'll pause here. There are several other questions on this worksheet that are similar. Okay, they're basically dealing with reactions. You might have to balance an equation and then set up unit multipliers in the way we've shown here to solve the problems. Good luck with that.